Hello, my name is Gabriel Cohen, and today I will be talking about the assignment 3, which was analysis of faces. So, starting off, we have how to identify faces at 9,000 degrees Celsius. So, first you identify a point that corresponds to 80% copper or 20% silver. And then in the graph you find the intersection point of 900 Celsius, and this intersection point of 80% copper will lie within the beta or the liquid plus liquid region, and the conclusion of this is that basically the alloy consists of two phases. It's the liquid phase and the beta solid phase, as you can see here. And then we can use the lever rule. And then in the lever rule, you can find the liquid phase weight fraction, which basically tells you if it's a liquid or a solid beta. Then you have a heat treatment, which varies between normalizing heat treatment and annealing heat treatment. So in annealing heat treatment and in normalizing heat treatment, the basically the you cool the alloy rapidly by removing it from the surface and letting it cool it in just air. And the microstructure of this is that the rapid cooling will lead to a smaller grain size, and it's more fine, it's more uniform, because it's a quicker solidification. And then this because it's smaller in grain size, it gives it increased strength and increased hardness. But the downsides of this is because it's really densely packed grains, it reduces ductility and it has less flexibility. And you have annealing, which in annealing you cool the alloy slowly inside the furnace, and by letting the temperature decrease gradually, what you're doing is that it allows larger grain growth, and it results in a coarser grain structure, which it works the opposite as the normalizing. It increases ductility and reduces internal stresses, but it lowers strength and hardness. Then you have the composition optimization, which basically it's like a strength versus concentration in the left chart, and you have ductility versus concentration in the right chart. And to achieve a strength of at least 190 to 200 MPa, for example, here you could find the weight percent of copper, like 55, right, percent. Or let's say you wanted to go to let's keep it simple, 170 MPAs of weight, megapascals. You would just you're at 0. That's the y-intercept. And then to maintain ductility, as you can see here, it's just a weight and ductility. So an elongation versus weight percent. So for example, if you wanted to have an elongation of 40%, it would be 28% copper. And you would want to find an ideal concentration right between these, which I'd say is around 45, given that the troughs or the peaks are there. And then here are the steps to alter an alloy's concentration. So you have the starting point, which you start at room temperature, and then you use the heating with a furnace, and you heat it to 1200 Celsius. Then you adjust the composition between silver and copper in the alloy. Then you mix it well enough so it's homogeneous, and then you cool it down. And yes, that's the presentation for today. Thank you.